A steel-gray hull, a Burke-class destroyer, cuts through the Gulf waters. Its Aegis radar sweeps the horizon, a multi-billion-dollar system engineered for global reach. Such a platform represents unparalleled technological superiority designed for dominance across vast oceans. Now, shift focus to the Strait of Hormuz. At its narrowest, a mere 21 miles wide. Beyond mere geography, it serves as a critical choke point, a bottleneck for 20% of the world's daily oil supply. The United States Navy possesses overwhelming power in this theater, a force unmatched by any regional adversary. Yet, these very destroyers, the backbone of its surface fleet, rarely operate within that critical funnel. It remains a profound operational paradox. Why does the most powerful navy on Earth treat this vital, constricted waterway as a virtual no-go zone for its most versatile surface combatants? Conventional equations of naval power do not align with this observed pattern. Examine the math. The utility of a multi-billion-dollar open ocean warship optimized for blue water engagements drastically changes when confined to a 21-mile corridor. The cost of potential attrition, the calculus of exposure to asymmetric threats, fundamentally alters the operational value proposition. Decisions rely not on sentiment, but on calculated risk. Traditional naval power logic posits a simple truth: more ships, more control. That equation breaks down in the Strait of Hormuz. Control is not about tonnage nor missile tubes. It is kinetic energy density per cubic mile of water. Destroyers are purpose-built for blue water operations. Their engineering optimizes for vast distances. For open ocean engagements, reach and endurance remain paramount. They function best across expansive horizons. In a confined, literal space, these strengths become critical liabilities. Deep draft, large radar signature, reliance on long-range sensor data, these are vectors for asymmetric exploitation. The operational utility curve inverts. It creates a geometric constraint. Their optimal performance window narrows to zero. The theater of operations here is dictated by stark physical limits. Geography serves as the primary constraint rather than naval power. The strait narrows to just 21 miles at its pinch point. Navigable channels are considerably tighter, constrained by depth and international law. Such regions differ from the deep blue water where destroyers thrive. The seabed rises, creating a shallower domain. Thousands of civilian vessels, from tankers to fishing dhows, transit these waters every single day. Their presence generates immense clutter. Radar pictures lack clarity. Acoustic signatures remain obscured. Lines of sight are rarely unimpeded. This constant, dense traffic creates an operational environment saturated with noise. It is a battle for signal over chaos. The sheer volume of non-combatant movement fundamentally alters targeting algorithms. Every contact requires classification. Every decision carries collateral risk. Far from an empty chessboard, the area functions as a maze of moving parts, a system designed for commerce, weaponized by its complexity. Iran's asymmetric equation relies on a distinct set of axioms. Parity is not their objective. Vulnerability is their target. Their doctrine acts as a deliberate countersystem engineered for the strait's constraints. Primary tools are not high-end platforms. They are distributed, agile, and numerically significant. Fast attack craft form the core. Hundreds of them exist, designed for overwhelming saturation rather than precision engagement. Such realities shift the defensive calculus. These craft are complemented by extensive, covert mining. Deployment is swift, designed for rapid waterway denial. Mobile coastal anti-ship missile batteries add another layer. Hidden, transient, they remain ready to engage targets. Individually, these systems are low cost. Collectively, their operational impact multiplies. Kill chains are short, localized, and redundant. The objective remains to overwhelm, flooding the sensor and engagement space. Such is the brutal arithmetic of access denial. Consider the apex of naval air defense, the SM-6 missile. A multi-million-dollar interceptor, it is engineered for advanced aerial and ballistic threats. It represents the pinnacle of layered fleet protection. Now, evaluate its application against a $20,000 explosive-laden drone boat. The cost exchange ratio becomes an unsustainable variable. One missile for one craft. The trade lacks balance. The system is bleeding resources. The ledger shows immediate, profound imbalance. A warship's vertical launch cells are a finite resource. A deep magazine exists, certainly, but it is not infinite. It cannot sustain a point defense exchange against an endless, low-cost wave. The physics of attrition will always favor the massed, inexpensive threat. Success depends not on heroism, but on inventory management. We do not engage in target practice. We engage in resource allocation. The hard data demands a different solution entirely. Aircraft carriers embody global power projection. These vessels deliver strategic reach across vast ocean expanses, providing sustained air power as mobile bases for any contested zone. Their very presence signals diplomatic intent, a formidable declaration of force without firing a shot. Such platforms are engineered for the blue water, for unrestricted maneuver. However, insert that same system into the Strait of Hormuz, and the variables shift dramatically. A multi-billion-dollar vessel becomes a high-value, slow-moving target. Its operational envelope shrinks as the geometry of the strait compresses its defensive perimeter. Maneuverability is crippled by commercial traffic and constrained depth. This environment negates every primary advantage a carrier offers, while amplifying every inherent vulnerability. The immense investment and capability are rendered suboptimal. The risk profile skyrockets while the utility plummets. Such a platform is not a force multiplier here. It is a liability, a misapplication of a capital asset. The operational calculus dictates a different approach. Forget larger platforms, faster speeds, or exponential cost. The optimal outcome emerges from smaller, smarter, persistent systems. Unmanned surface vessels maintain constant watch, performing persistent intelligence, surveillance, and reconnaissance. No human life is risked. Continuous presence is achieved without crew rotations or a heavy logistical footprint. Unmanned underwater vessels operate below the surface for covert surveillance and mine detection. Unseen and unheard, they extend the sensor grid into denied spaces. For rapid interdiction, the calculus shifts again. Fast patrol boats offer superior cost per hour, and their survivability profile for this specific environment is significantly better. Designed for focused, high-speed engagement, they function as expendable assets rather than capital ships. Consider the brutal arithmetic. A single patrol boat costs a fraction of an Aegis destroyer. Its loss is an operational setback, not a strategic blow. This represents how we optimize for the variable of constrained waterways. The Strait of Hormuz demands a specific operational architecture based on a multi-echelon defense. We implement a three-layer filter. Layer 1, persistent detection. This constitutes the foundational sensor grid. Unmanned surface vessels maintain tireless watch, while unmanned underwater vehicles map the subsurface topography. Shore-based radar arrays provide comprehensive, low-altitude coverage. This creates a continuous, low-cost awareness mosaic. Blind spots are eliminated, ensuring no unmonitored transit. Layer 2, asymmetric denial. This layer disorganizes incoming threats. Mine warfare capabilities restrict enemy maneuver, while advanced electronic warfare systems jam communications and spoof navigation data. Small, agile interdictors harass and redirect. Their objective is disruption, to break formation and induce chaos within a massed attack. Layer 3, precision destruction. This localized kinetic response relies on assets optimized for the cost exchange ratio. Forget blue water destroyers or multi-billion-dollar platforms. A single destroyer's missile load exceeds the value of an entire small boat fleet. The equation favors numerous inexpensive effectors. They deliver targeted kinetic effects, eliminating specific threats without expending disproportionate resources. Managing the variable of economic viability and conflict requires this specific approach. The decisive variable in this theater is the ratio of reaction time to target density. A single high-value platform, like a destroyer, faces an impossible engagement timeline when confronted by a swarm. Its sensors track, its combat system processes, and its launchers fire. Each cycle consumes precious seconds, yet the incoming threats multiply. A destroyer cannot acquire, track, and engage dozens of targets simultaneously without quickly depleting its magazine. Such limitations represent a fundamental constraint of physics and logistics rather than a failure of technology. The time required for individual engagement exceeds the rate of threat generation. Brutal arithmetic reveals a critical vulnerability. One missile fired per target is an unsustainable expenditure against 100 threats. The system fails not due to lack of capability, but due to an unfavorable numerical exchange. Optimal solutions point toward distributed, low-signature assets, systems that can absorb hits, rapidly disengage, or remain simply too numerous and cheap to justify high-value missile expenditure. Success depends on optimal system deployment rather than raw power. Deploying high-value destroyers within the Strait of Hormuz is not a question of capability, but a deliberate operational decision rooted in a prohibitive cost-benefit analysis. These vessels are engineered for open ocean engagements, optimized for entirely different variables and operational equations. Their primary design function addresses a distinct threat matrix and a unique set of mathematical challenges. The answer to our implied query remains simple: prudence. It is a strength of calculation, not a weakness of will. We reassess the assumptions, recognizing that the common perception of more firepower as a universal solution is precisely where the math resets. This operational constraint derives from a fundamental model: the sum of localized geometry, asymmetric threat profiles, and the inherent cost-exchange ratio dictates the viable deployment envelope. Their absence is a feature of optimal resource allocation, not a deficiency in resolve. Because their mission parameters are distinct, we do not worship the machine, we worship the equation.